So our first talk is going to be given by Jim Head and colleagues, and the title will be Geologic Context for Lunar South Circumpolar Region Exploration Implications for Goals, Site Selections, and Operation Strategy. Take it away, Jim.
Okay, thank you very much, Hannes and Noah. This is an incredibly exciting session because we're really taking a look at some of the broader aspects of the South Circumpolar region, which is the destination, of course, of a whole armada of international spacecraft in the coming decade. So let's first take a look at the characteristics of this international focus. Why are we doing this? Okay, well, the first thing is, of course, it's a scientific desire to get outside of the wonderful Apollo Luna Chang'e 3-5 region of the central northern near side, and also to really be able to try to address some fundamental questions we haven't necessarily been able to do before, which have a lot to do with fundamental aspects of the formation and evolution of the moon, particularly its early history. And most importantly, perhaps, is the role of the South Pole Aitken Basin, which you can see here. I should point out a third point here, which is if all the volatiles were located, maybe by True Polar Wonder or something, located here on the far side, we would not be going to those areas necessarily. We would not be establishing a base there because the reason we're going to the South Pole is fundamentally that we cannot survive lunar night. We need to be there with constant illumination. So keep that in mind because whoever cracks the code of surviving lunar night owns the moon. And I think it's up for grabs, okay? So just keep that in mind. So let's talk about what I like to call the bedrock geology, which is a really kind of a misnomer for the moon. But we really want to know the provenance. Where did these rocks come from? We want to identify the major sequence of events and really assess what this means for the primary scientific questions that ones have to do with non-volatiles in this particular case. That's the focus here. And then what we need to do is think about how these influence human robotic exploration strategy, because our acquisition of answers to these fundamental questions is only as good as our ability to plan traverses, to train astronauts, and to extract the correct data. So let's think about this, but first let's talk about what is so important. First of all, the global context. This is an unexplored region providing access to the far side and two major relatively unexplored lunar crustal terrains, the far side highland terrain and SPA that Brad Jolliffe described some years ago. It also gives us insights into the sequence of events because, in fact, we're looking at the post-crustal formation, 2,500 kilometer diameter South Pole Aitken Basin, and then, of course, all the features that have formed subsequent to that time, a whole slew of impact basins. If we could date these, particularly SPA and these other basins, then we have an opportunity to really deconvolve not only the signal from the moon and the origin and evolution of the moon, but the chronology for the solar system. So the South Pole location is indeed, the center is located at the South Pole, of course, within the SPA outer ring. And, you know, this is equivalent to the Oriental Cordillera ring, but due to the multiple subsequent impacts, as you can see in the geological map here, and the overlapping ejecta here, this is really a hard nut to crack. It's more similar to the Apollo 16 Central Highlands complex impact polymeric breccia dominated geology than to things we're used to before, like Apollo 15, 17, 11, 12, and 14, for example. So strategy, you know, what we need to do is deconvolve this complex SCR history. This really presents a formidable challenge and requires an integrated strategy for site selection, traverse planning, sample assessment, et cetera, et cetera, et cetera. So let me try to outline a few of these points here. First of all, the South Pole Aitken Basin ejecta mantle sampling paradox. Hey, we're going to the rim of the basin. That's where all the good stuff is. Well, maybe not, okay, because SPA is likely to have been a oblique impact. Here's the South Pole, and most of the, particularly the deeper ejecta, is likely to be, in fact, in the distal part, not the proximal part. So we have to be very careful here and very selective and try to understand where that might be. If the South Pole Aitken Basin rim contains any mantle material, the most likely sampling locality is a steep-sloped Mons Malapart here, and it'll probably occur as admixed, small breccia fragments admixed further by subsequent impacts, of which there are hundreds, okay? So we really need to be thinking ahead here about how we're going to carry this out. What about the geological stratigraphic framework? Well, there's good news and bad news. The topography is dominated by the SPA Basin outer ring, but that's here, okay, there it is. But it's complicated by multiple subsequent overlapping impact ejecta deposits. As I pointed out, it's most like Apollo 16, the Descartes Highlands. Detailed local geomorphology, like at Apollo 15 or Apollo 17, provides minimal, if any, clues to impact multiple polymeric breccia provenance, okay? So we have to figure that out in a separate way. So in the SCR, 20 plus kilometer diameter craters, as you can see here, interleaved ejecta deposits, as we showed before in the ejecta overlap, at all scales dominate walking traverse and probably rover traverse sampling. So we need to be really careful and focus on how we're going to optimize this with the best possible mission plans. So a really critical part here is determining basin crater absolute chronology. We need a regional sample, but look at all these different craters here. We need a representative sample, and we also need to collect any exotics. If we're going to only be walking around for a short distance on the early missions, then in fact, we need to have a rake, okay, to get a very important representative sample, but also sample exotics thrown in from other places. Another point here is we'll be mapping secondary craters to get these other basins. If we're looking at a regional area, you know, of the order of radius of a kilometers or maybe 5 or 10 kilometers.
6
So
minutes.
shock secondary craters and clusters from different basins, for example, from Oriental, are really going to be what we're going to have to use. Here's a map of all the craters greater than a kilometer post-Oriental, the youngest of the basins. This is, you know, horror show, okay? And not only that, they're not symmetrical secondary. So as you can see here from this work by Guillaume et al. So again, another part of it that we have to point out in detail, work on in detail. Pinpoint landing is necessary to ensure access to targets of crater basin ejecta, secondary and South Pole Aiken Basin mountains. We can't just land anywhere here. Look at all these different craters. They're all going to have overlapping ejecta. We need to understand that. Traverse design and mobility. If we take a look here, basically there are two major requirements that derive from the South Circumpolar region geology. Due to its complexity, okay, the time at individual sampling stations will be long, and the learning discovery intensive, the learning curve is going to be discovery intensive relative to Apollo. And this has a lot of meaning in terms of astronaut training and traverse design and mission planning design. We need mobility. Greater than Apollo 15, 17, tens of kilometers is required. And any kind of design reference mission CONOPS actually might feature long radially oriented traverses with multiple widely spaced long duration stations, fresh blocky craters such as those at North Ray on Apollo 16, and rover design should exceed the design performance of Apollo Lunicod, because in fact, Apollo Lunicod cannot safely access Mons Malaparte over most of its surface, okay, as shown by Vasilevsky and others. So sampling procedures we need, okay, if we can't just sit there and triage polymeric breccias, okay, we need real-time handheld remote sensing capability to identify fingerprints such as mafic minerals, ultramafic, creep rich, etc. We need tools to ensure representative and diverse samples such as a lunar rake. We need mobility to determine the regional petrological variability such as a lunar rover, and we need large sample return mass. Everybody get onto the Artemis program to increase the up mass and return mass, which is currently less than 50 kilograms per mission. Okay, here's where that lies in the overall scheme of Apollo, when you include sample return containers and things like that. That's a key issue that needs to be resolved. So finally, mission operations and science support, okay? There's a very steep on-site learning curve, okay? This is for the astronauts, okay? They will be learning a lot fast. This means that basically, remember the Apollo T-cube strategy, train them, trust them, and turn them loose. The situational awareness will always be with the astronaut on the ground. So the ground needs to develop a backroom psychology, which is kind of an advisor consultant psychology. And we need this because when we go to Mars, which is what we're practicing to do, crew autonomy is required. Okay, so let's go. There's tons of things to do, but we have a big challenge in terms of how we operate on the surface with these major constraints. And key among those is astronaut LRV mobility in order to get away from the walk-back constraints and really optimize this. Thank you very much.
Thank you, Jim, for an awesome talk.